We've seen this reaction before. This is the decomposition of nitrogen dioxide to nitric oxide and oxygen. And we've already proved it's a second order reaction, and we also found the rate constant at 300 degrees C. So in part A, if the initial concentration of nitrogen dioxide is 0.008 molar, what is the concentration of nitrogen dioxide after 20 minutes? Well, we know this is a second order reaction, so we can use our integrated rate law for a second order reaction. And that was 1 over the concentration of A minus 1 over the initial concentration of A is equal to the rate constant K times the time. So this is one form of our integrated rate equation. And let's think about what we're going to plug in here. We're trying to solve for the final concentration of NO2. So we're going to put in here 1 over the concentration of nitrogen dioxide at 20 minutes. All right, this would be minus 1 over the initial concentration of nitrogen dioxide, which is 0.008. So we plug that into here. So 1 over 0.008. This is equal to our rate constant, which is 0.54. So we have 0.54, 1 over molar times seconds. And then we're going to multiply that by the time. Notice we have seconds here for our rate constant. We were given minutes. So we need to convert minutes to seconds. So if you have 20 minutes, right, we know that there are 60 seconds for every 1 minute. So if we multiply, minutes cancels, and that gives us seconds. So 20 times 60 is 1200. So we have 1200 seconds. All right, so let's go ahead and let's do the math. So let's get out the calculator here, and we'll multiply 0.54 by 1200. And so on the right side, we have 648. So we have 648. Notice your units, right? Your seconds would cancel here. And the left, what's 1 over 0.008? Right, so let's do that. What's 1 divided by 0.008? That gives us 125. So we have 125 here. We have our minus. This would be 1 over the concentration of NO2. All right, so now, of course, we're just solving for the concentration of nitrogen dioxide. So 1 over the concentration of NO2 is equal to 648 plus 125. And that, of course, is 773. So to solve for the concentration of nitrogen dioxide, that would be 1 over 773. So let's get our calculator out, and let's do 1 divided by 773. And so the concentration would be 0.0013. Right, so this is equal to 0.0013 molar. So if you start with a concentration of 0.008 molar, the concentration after 20 minutes goes down to 0.0013 molar. All right, let's move on to part B. So in part B, if the initial concentration of nitrogen dioxide is 0.008 molar again, what is the half-life? So in the previous video, we talked about the equation for the half-life of a second-order reaction. And we found that the half-life for a second-order reaction is equal to 1 over the rate constant K times the initial concentration of A. And so for this case, right, this would be 1 over the rate constant, which is 0.54. 1 over molar times seconds. And then we need to multiply that by the initial concentration of A, which of course would be the initial concentration of NO2. So that's times 0.00800 molar. All right, so let's do that math. So we get out our calculator here, and we take 0.54 and we multiply that by 0.008. So we get 0.00432. And so we take 1 divided by that, 1 divided by our answer here, will get us our half-life. So we get 2.3 times 10 to the second seconds, right? So this is equal to T1 half is equal to 2.3 times 10 to the second seconds. Or we could say approximately 230 seconds. Right, so approximately 230 seconds. So if we're going from a concentration of 0.008, right, if we're going from a concentration of 0.008 molar, right, and we wait approximately 230 seconds, the concentration goes down to 0.004. So we have half of our initial concentration after one half-life. All right, let's compare what we got in B to what we're going to get in C, because in C we're changing the initial concentration of NO2 to 0.004 molar. So now what's the half-life? So the calculation is the same, right? We're going to plug in T1 half is equal to 1 over K times the initial concentration of A. The difference is we're changing the initial concentration. Right, so K stays the same, so 0.54, 1 over molar times seconds. But now we're going to plug in 0.004 instead of 0.008. Right, so we have 0.004 molar, and we're solving for the half-life. So once again, we can get out our calculator here, take 0.54, multiply that by 0.004. And then if we take 1 over our answer, then we should get our half-life. So that's 4.6 times 10 to the second. All right, so this would be equal to, all right, so our half-life would be equal to 4.6 times 10 to the second seconds, right? So this is seconds. So I think I forgot to point that out in the previous example, right? If you're looking at your units, right, the molar would cancel here, and so you'd have 1 over seconds, which of course is equal to seconds. So the half-life is measured in seconds. It'd be the same thing for up here, right? The molars would cancel. We'd have 1 over seconds, so we get seconds here. So this half-life, 4.6, let me just make this look more like a 6, 4.6 times 10 to the second, that's twice our first half-life. Right? So if we're going from a concentration of 0.004 molar, and we wait approximately 460 seconds, right, we're going to end up with a concentration of 0.002 molar. So remember, for a second order reaction, the half-life is not constant, right? So we talked about this in the previous video. The half-life for a second order reaction depends on the concentration that you're starting with. Right, and so we can see here, right, we're starting with a concentration that's half of the first one, and we can see that our half-life is twice as long. So this second half-life here is twice as long as the first half-life that we talked about for part B.